In the last video, we looked at what an inverse was, the definition of an inverse, and we did an example of finding the inverse. So let's go ahead and do another example of finding the inverse. So let's find the inverse of f of x equals x cubed, and then we're going to graph f of x and f of x and its inverse on the same graph. So let's see if we can do this one a little bit quicker than in the previous video. So we have f of x equals x cubed. Alright, the first step in finding the inverse was to replace f of x with y. So we have y equals x cubed. Then we interchange x and y. So that means x equals y cubed. Next we have to solve for y. This one's not too bad. We take the cube root of both sides and we end up with the cube root of x equals y. We took the cube root of both sides. And then we replace y with f inverse. So f inverse of x equals the cube root of x. And so there's our inverse. Okay, so let's go ahead and graph these. Now, x cubed was one of our parent functions, so we know how to graph that. It looks something like this. There we go. So this is f of x equals x cubed. Now the cube root of x, that one you might have gotten in Algebra 2, but the cube root of x basically looks like this. So there's f inverse of x equals the cube root of x. Okay, so now that we've done another example of finding the inverse of a function and graphing the inverse and the original on the same graph, you might be wondering if there is some kind of relationship between a function and its inverse. And there is a relationship. And we can kind of see it in the graph. If you go back to your notes from the previous problem, you'll probably notice, hey, there looks like there's some relationship there. And what happens is, when we look at the graph of the original and its inverse, it's symmetric. And it's symmetric over a line, but it's not the x-axis or the y-axis. What we do is we have to sketch in this diagonal line. And that's technically the line y equals x. And once I sketch that in, then it's, I think, a lot more obvious that these, the inverse, the original and its inverse, they're related because they're reflected over the line y equals x. And so that'll be true for any graph and its inverse. So let's write that out. The graph of an inverse function is the graph of the original function reflected over the line y equals x. So, an inverse, a function and its inverse do have symmetry. Right, so now if this is true, I guess we can look at the idea of what if you're just given the graph of a function and you need to find the inverse of it. And if that's a problem given, or if that's the situation you have later on in mathematics, then there is something you can do to find the graph of the inverse. So let's look at an example of that. Let's use the graph of the function to sketch a graph of the inverse. All right, so in this problem there is a graph that we're going to work on. All right, so here's the original, and I'm going to write down 3 points. So we have 1, 2, 0, 1, -2, 1/2. And it's going to look something like that. So here's our original function, f of x, and so we had the points -2, 1/2, 0, 1, 1, 2. All right, so this is what's given. We have this graph and we want to sketch a graph of the inverse. Now, the issue is we don't have an actual function. We don't have an equation to work with. So we can't do what we did up here, where we put in y, interchange x and y, and solve for y. That's not an option. And this actually is fairly applicable, because if you ever work in a field in science or something where you work with data, when you work with data, you're not going to have an equation. You're only going to have data. And so you might have, of course, you'd have many more data points than the 3 I gave you, but even if you have an infinite amount of data points, then you can even graph it on a computer or calculator, you're still not going to have an equation. But if you need to find the inverse, which oftentimes you do want the inverse, what do? And so it's pretty straightforward. So step 1, we're going to draw the line y equals x. So we're going to dot that in. There we go. Y equals x. And then step 2, we're going to reflect a few points. Now, if you have data points and you have thousands of data points, of course you'll reflect all the data points. But in this case, we only have a couple of points, so we're just going to reflect those few. And the key here is if you have a point, f of x, which has coordinates x, y, then the rule is f inverse of x has the points y, x. So all we need to do is take a point that's on the original and just switch them. So we have the point 1, 2. Well, when we switch them, it becomes 2, 1. If we have the point 0, 1, then we have 1, 0. And then if we have the point -2, 1/2, we have the point 1/2, -2. So we were able to reflect all those points. And then step 3, once you gotta have as many points as you either are given or you need, we then sketch the graph. Sketch a graph of the inverse. And so you kind of have to look at what you have, and you have to imagine, okay, I'm reflecting this thing over the line y equals x. And so it's got to look something like this. And then let's label these points. We have 1, 2, so now we have 2, 1, 1, 0, 1/2, -2. Okay, so in this video we went over another problem, an example. We then drew the graphs, and really the big thing with this was we noticed the relationship that an inverse and the original function have, and that they are symmetric. They're symmetric over the line y equals x. And then we looked at an example where if you're only given the graph and a couple data points, how do you graph the inverse?